So in the Schrödinger model of the atom, electrons are located within electron shells, which are inside which we will find electron subshells, and inside those subshells we will find orbitals. So the important thing to recognize is that subshells are found within shells, orbitals are found within subshells, just like cities are found within states, and streets are found within cities. So as we go down here, we're getting a more precise description of where the electron is. So the shell is the least precise description of where the electron is located that we can give in the quantum mechanical model. Electrons in the same shell spend most of their time at similar distance from the nucleus. And as we go to higher shells, we move further and further away from the nucleus, and that corresponds to higher energies. So if you like, shells are kind of like layers of electrons. Now you can see that these shells get larger in circumference as they get bigger and bigger. And so what that means is that the higher shells can contain more electrons than the smaller ones. So we designate the electron shell with the letter N, and the maximum number of electrons that you can find in any particular shell is just equal to 2n squared. So in the first shell, it has n equals 1. The maximum number of electrons that can be found is 2 times 1 squared, or 2. In the second shell, which we give the designation n equals 2, we can find 2 times 2 squared, or 8 electrons. In the third shell, with n equals 3, 2 times 3 squared, 18 electrons. So you can see, as we go to bigger and bigger and bigger shells, we can put more and more electrons in them. So electrons that are in the same shell have a similar distance from the nucleus, or a similar energy. As we move to higher shell numbers, we're kind of moving to other layers of electrons, to larger layers of electrons. So the electron shell is indicated by a positive integer, so 1, 2, or 3, and the maximum number of electrons that can be accommodated in a particular shell is given by the formula that the maximum number of electrons is equal to 2n squared. So within shells, we have these things called subshells. Now remember, as we go from n equals 1, n equals 2, n equals 3, as we increase the shell number, these guys get bigger. The shells get bigger, the layers get bigger, so we would expect more subshells. Okay? Just like within a bigger state, you get more cities. So electrons occupy regions of space called subshells within each shell. Electrons within a given subshell of a shell have the same energy. And the subshells are of 4 different types. There is S, P, D, and F. And they are increasing in size. S subshells can hold a maximum of 2 electrons. P subshells can hold a maximum of 6 electrons. D subshells can hold a maximum of 10 electrons, and F subshells can hold a maximum of 14 electrons. Now, I mentioned previously that as we increase the shell number, the shells get bigger, so therefore they can accommodate more subshells. So the first shell is fairly small, and it can only accommodate 1 subshell, and that's an S subshell, and that can hold 2 electrons. The second shell is a little bit bigger, so therefore it can hold 2 subshells. It can hold an S and a P. And as an S subshell can have a maximum of 2 electrons, and a P subshell can have a maximum of 8 electrons, that means in the second shell, we can have a total of 8 electrons. When we go to the third subshell, it's bigger still, and it can have 3 subshells in it. An S subshell, a P subshell, and a D subshell. And keeping in mind that we can put 2 electrons in an S subshell, 6 electrons in a P subshell, and 10 electrons in a D subshell, this gives us a total of 18 electrons that we can put into the third shell. Now, when we get to shell 4 or higher, we can have the full set of 4 subshells. So that means that we can have an S, a P, a D, and an F. An S can hold 2 electrons, a P can hold 6 electrons, a D can hold 10 electrons, and an F can hold 14 electrons. So adding all of that together, we've got 8, 18, plus another 10, that's 28, plus 4, we can put 32 electrons into shell number 4. Now, beyond shell 4, they all have this full set of the 4 different types of subshells. Now, you can see here how we're indicating, how we're notating a particular subshell. We're writing the N value, and then we're writing the letter S, P, D, or F that indicates the type of subshell. So that's telling me exactly where the subshell is. That's the shell number, and then that's telling me what type of subshell it is. Later on, we're going to put a number here that's going to be the number of electrons that is in that particular subshell. Okay, so subshells describe regions of space within a shell. The number of subshells a shell has is equal to the shell number. So the first shell has 1 subshell, the second shell has 2, the third has 3, and the fourth or higher has a full set of 4 subshells. The subshells are of 4 different types: S, P, D, and F. An S can hold a maximum of 2 electrons, a P can hold a maximum of 6, a D can hold a maximum of 10, and an F can hold a maximum of 14. So within subshells we find orbitals, and orbitals are a region of space within a subshell. Now we know that an S subshell is fairly small. It can only have 2 electrons in it at most. A P subshell is bigger. It can have 6 electrons. A D subshell is bigger again. It can have 10 electrons. And an F subshell is the biggest. It can have 14 electrons. So we would be expecting, as we move through this series of subshell types, we're going to be having more or an increasing number of orbitals. So electrons occupy regions of space called orbitals within every subshell. An orbital describes the region of space within a given subshell where an electron is most likely to be found. The maximum number of electrons that can be placed into an orbital is 2. So S subshells have 1 orbital. That's why you can put a maximum of 2 electrons in an S subshell. A P subshell has 3 orbitals. That's why you can put 6 electrons into a P subshell. A D subshell is bigger again, and it has 5 orbitals. That's why you can put 10 electrons into a D subshell. And an F subshell is even bigger. It has 7 orbitals, and that's why you can put 14 electrons into an F subshell. So the different types of subshells have characteristic shapes. So the orbitals of an S subshell are kind of spherical, all right? Spherical in shape. And these spheres increase in size as the shell number increases. So, a 2s is bigger than a 1s, and a 3s is bigger than a 2s. The orbitals that are found within a P subshell have this weird kind of 2 teardrop shaped kind of arrangement where we have 2 teardrop shaped lobes that touch at their pointy ends. There's 3 of these and that make up a p subshell, and they're oriented at 90 degrees to each other. So one of these orbitals is oriented along the x-axis, one is oriented along the y, and one is oriented along the z. Now d, there's 5 of these guys, 5 times the d orbitals, and there are also and there are 7 f orbitals that make up an f subshell, and they're pretty complicated shapes. Now the d orbitals typically have this sort of like 4-leaf clover kind of shape, so they're kind of like 2 p orbitals pushed together, and then f orbitals normally have at least 8 of these lobes that are kind of quite complex in their orientation. So generally, if you're given a diagram, you can tell the difference between an s orbital, a p orbital, a d orbital, and then an f orbital where it just gets kind of crazy and we have like lobes going everywhere. But if you were given a picture, you should be able to tell the difference between those different types of orbitals. Now, an orbital describes where an electron will be found or is likely to be found. What it doesn't describe is how the electron is behaving. And what Schrödinger discovered is that the electrons that are found within these orbitals behave as though they are spinning. Now, when charged particles spin, they create a magnetic field. But the interesting thing about the magnetic field of electrons is that it is quantized. It only ever has 1 or 2 of 2 possible values. The electrons behave as though they are magnets with their north pole either pointing up or their north pole pointing down. We describe this as being either spin up or spin down. And we can see this if we take a beam of atoms that contain only 1 electron, like a beam of hydrogen atoms, and we pass this between the poles of a magnetic field, we will find that rather than them behaving as though they had their magnetic poles randomly oriented, they behave as though their magnetic pole is either pointed up or pointed down, and they just split into 2 nice groups. So we can talk about what an electron is doing within an orbital, how it is behaving, and in particular we're going to talk about how it is spinning within an orbital. So the region of space an electron occupies about an atom is described by its shell, subshell, and orbital, each having an increasing precision. The shells kind of correspond to layers of electrons. The maximum number of electrons in a given shell is given by the formula 2n squared, where n refers to the shell number. There are 4 different types of subshells designated by the letters S, P, D, and F, and they are of increase in size. Every subshell is comprised of 1 or more orbitals. S subshells have 1 orbital, P subshells are comprised of 3 orbitals, D comprised of 5, and F subshells are comprised of 7 orbitals. The orbitals that are found within a subshell have a characteristic shape, and every orbital can accommodate a maximum of 2 electrons. We also know a little bit about how the electrons are behaving within those orbitals, and in particular, the electrons behave as though they are spinning, but that spin is quantized. It is either up or down.